All right, it's close enough to 11 and I'm getting bored just standing up here. This is Circuits 2. We're gonna spend today kind of talking about some of the basics of the class and some software packages I'm gonna expect you guys to use and all that kind of jazz. And then we're gonna get into the real nitty gritty, as it were, on Friday. So first things first, I'm up here on our course's Moodle page. If you have to miss class, I will be recording all of our, or I guess simulcast, or whatever you want to call it. So I'm recording all of my lectures to Zoom. So if you're physically unable to attend class, you could join virtually using the link on the left. And then I'll also be uploading all of the videos to YouTube in case you have to miss and aren't able to attend physically or virtually. So all the material that will be presented throughout this class will be available to you. I have classes until 5 on Mondays and Wednesdays, so I'm probably going to do a lot of the uploading over the weekends. So it might be like all 3 classes will be put up Friday afternoon, or all 3 videos will be uploaded to YouTube and then the Moodle page on Friday afternoons or Saturday mornings or something like that. So just bear with me because my schedule's crazy. My office hours are from 7:30 a.m. to 9:30 a.m. and 12:30 p.m. to 2 p.m. We can either do it physically in my office upstairs, Nethkin 211, or virtually through this other Zoom link that I have put up here. So whatever way floats your boat. And then I have a link to all of my videos and all that crap I created for Engineering 221. So in case we're doing current division or something like that, and you don't remember exactly what the rules or algorithm is, instead of me wasting 30 minutes reteaching you, I'll tell you, hey, go watch the video on your own time, and then we'll jump back into it. All right, so that's all available in the introduction section. Class meeting 1 section, we have our syllabus. That's the first thing that we're going to discuss. It's going to have some of the same information, so who I am, where you're at, all that kind of jazz. My office hours, my email address. In the event of another global pandemic or snowpocalypse, we will be having class on Moodle. The course objectives is to enhance what you learned in Engineering 221 into more complex circuit analysis. The textbook is officially Engineering Circuit Analysis 9th edition by Height, Kimmerly, and Durbin. Unofficially, any circuit textbook will do. I will never ask you to work something out of a specific textbook or anything like that. So anything is useful while I have the internets up. I know this is not the official textbook for the class by any stretch of the imagination, but if you Google CAD and ULABI, it will tell you that you're misspelling it. You are not. This is a textbook out of the professor at the University of Michigan is providing for free. So it's a free PDF copy, or it's $75 if you want a hard copy of it, which just covers the printing costs and all that kind of jazz. It is actually a very, very good textbook, perfectly available to you for free, so you don't have to feel bad about stealing stuff. So just wanted to let you guys know of that. I really like the way that this textbook teaches the RLC circuits that we're going to be covering in a couple of weeks. I'm less enthused about the way that it teaches 3-phase power, but it does get the job done. So if you want a free textbook, here one is. All right, disability disclosure. If you need testing accommodations or anything like that, please let me know and the Department of Testing and Disability Services know as soon as possible. Class attendance. Officially, it's whatever the university bulletin says. Unofficially, you're adults. You can show up to class if and when you please do so, either physically or virtually. I will take attendance every day because I'm required to do so. I will not hold your crappy attendance against you. Your test scores will probably do a good enough of a job of that for me. If you're able to make an A on every exam and stuff in this class without ever showing up, congratulations, you deserve an A in the class. So I'm not gonna penalize you for not showing up. I don't know what you got going on. You're adults, you make those type of decisions. Academic misconduct, officially, more stuff from the bulletin. Unofficially, if I catch you cheating, I'm going to fail you. And as far as behavior and all that kind of stuff, if you're less of a jerk than I am, then we're going to be on great terms. Homeworks. There will be a selection of homework problems posted on the course's Moodle page at the end of each lecture. Not every lecture, but almost all of them. I think I'm anticipating 20 homework assignments. Homework assignments are due at 5 p.m. 1 week after they are assigned and must be properly formatted as detailed on the course's Moodle page. We'll check that in a second. Any homework assignment submission that does not adhere to the format detailed will be rejected from grading, meaning I have told my grader not to grade them. Late homework assignments will incur a 20% penalty for each day that they are late. So while we have homework on our minds, I have posted here in the class meeting #1 section a homework formatting example. I want to spend maybe 2 or 3 minutes going over it with you. I will happily answer any questions you may have, and then I will consider that this issue has been covered. So my expectation for you on your homework assignments, not all of them will be 31 pages like this one is. Probably most of them will not be even near that. Is that you will use the assignment sheet, which is uploaded as a PDF file on Moodle, as your cover pages. So there's problem 1, problem 2 and 3, 4, 5, and 6. So it's just the assignment sheet is the first few pages. Then my expectation, this thing will scroll, is that you will solve the problem using proper engineering format. I hand wrote out the problem statement and all that crap again. I do not require that you do that. You can, and so what I mean by that is you can make a copy of it from the PDF or whatever you want to do so that you don't have to waste 30 minutes just writing crap by hand that's redundant. But I do want it in the proper engineering format where it's the problem statement and then the solution, etc. So here is problem 1 in proper engineering format, starting with the statement, then the solution. Answers for each subsection are boxed. You don't have to put these little things here. That's just me telling my grader how much these points or these parts of this particular question were worth. Just doing the whole thing. So for subsection B, there's the answer for that boxed. Subsection C, boxed, etc. Then immediately following the handwritten work for problem 1, I have included the computer work for problem 1 because I used a computer algebra solver to handle the math portion of my nodal or looks like mesh analysis, I say here. So that is the expected format. You have all of the assignment sheet, handwritten work for problem 1, computer assisted work for problem 1, handwritten work for problem 2, computer assisted work for problem 2, handwritten work for problem 3, computer assisted work for problem 3, etc. That's all this is. Your computer assisted work will either be MathCAD work like I have demonstrated here, or LTSpice work, which we'll talk about shortly. So does anybody have any questions regarding the homework formatting? I am an absolute ass about having it done correctly. I just want to be very upfront about it, okay? If you don't do it right, I'm just going to throw it away or tell my grader not to grade it until you submit it correctly.
Can you repeat what you said about the
Yeah, so I give you a digital copy of it. So instead of, so right here in the problem statement for problem number 2, what I said was you do not necessarily have to handwrite all of this stuff. You could copy the problem statement from the digital document and put that into your solutions, and I'm okay with that. Is that clear?
Yeah, like take a picture of and paste it.
Sure, or however you choose to edit your files. All the homeworks and stuff in this class will be submitted digitally. Whether that is you printing something out and then doing your work under it and then scanning it, or you doing it on a tablet where you can move stuff around as you see fit, whatever, your engineering students, you will figure that part out as far as I'm concerned. Yes, sir. I will only take digital copies. I do not want paper cluttering my life up. So you can do it, you can do it on paper and keep a paper copy for yourself or whatever. You do not turn paper into me. The paper turned into me has a chance of being either lost or having coffee spilled on it, or in some way, shape, or form being whatever. Digital copies, it's impossible for me to lose it. So that's why I prefer that. So if we go back to our courses Moodle page, just real quick, down here at the bottom, homework assignment 1, which is a review of some topics that are necessary to succeed in this class, there is already an online submission portal that will only allow you to submit PDF files, okay? A single PDF file. So you do all your work, put it all in the right order, scan it, or do whatever you got to do to put it into a single PDF, and then you upload it here using this particular format: your last name, comma, your first name, space dash ELEN 223, spring 2021, homework 1 PDF. Homework 2 will obviously be the same thing, but homework 2, et cetera, et cetera, et cetera. So it needs to be in a PDF file using this specific naming convention, also using this specific format of the assignment sheet comes first, handwritten work for problem 1, computer assisted work for problem 1, handwritten work for problem 2, computer assisted work for problem 2, etc. As you can see here, this is due March 17th, which is exactly 1 week from today, which is March 10th. Homeworks in this class are due at 5 p.m., so close of business. So that gives you 3-ish class meetings in 3 days of office hours for every homework assignment to come ask me questions about, am I approaching this correctly, or have I created this file in the correct format, or any of that kind of jazz that you want to ask me. I feel like I'm a stickler for when you finally turn it in, but I give you plenty of time, in my opinion, to ask questions and all that jazz so that you're not going to, I don't know, freak out and crap your pants before it's due. Does that make sense? Any other questions regarding the homework formatting and all that jazz? Raising your hand or stretching. No, it's not every Monday, Wednesday, and Friday. So let's pop back over to the syllabus if I can find it real quick. So jumping ahead here. These are a list of the dates you should expect to receive a homework assignment. So homework assignment 1 is on the 10th. Homework assignment 2 will be assigned on Friday, etc. So there are certain homework assignments. So like this guy right here, homework assignment number 5 covers both negative feedback circuits and common amplifier topologies, because that is largely a review of some stuff that was covered in circuits 1. And so it just felt redundant for me to make you rework a bunch of those style problems. Similarly, once we get down here, total response of general RLC 1 and homework assignment literally only has 2 problems. We just dedicate 2 days to it, because figuring out how to do the math isn't hard, it's just tedious, but once you get it, it's rather trivial. So things like that. Down here, this homework assignment is only on filters. So it will cover both the material covered in Intro to Passive Filters 1 and Passive Filters 2. There is not a homework assignment on the Introduction to Polyphase Circuits lecture, because that is mostly going over terminology and things like that. And so all of that will be covered in subsequent assignments. So it is not every single lecture, but it's 20 out of the roughly 26 lectures. So it's a lot of homework. Not all, some of the homework assignments are only 2 to 3 problems. Others are, 5 or 6. So it's a mixed bag of, some days you're going to be like, God, Dr. Hartman is a complete ass. And other days you're going to be like, this is not that bad. So, as is life in general, sometimes I'm a jerk and sometimes I am not. Don't know what else to say. Did that answer your question? What's up?
So in circuit 1, we watch maybe a 40 to hour long lecture in this class. How are we gonna do it in this class? We're gonna have 2 lectures we have to watch.
Nope. You show up, we talk about stuff. The only time I would do a YouTube lecture, I have recorded lectures for all of this stuff. So if in-person classes have to be canceled for whatever reason, I might ask you to watch a YouTube lecture instead. but I don't anticipate that having to happen. Right now, I am sweating profusely, so I feel like the chances of another winter storm event coming through are pretty low. And I'm getting vaccinated today, so I'll be showing up to all classes in person for the remainder of the quarter. Whether you choose to show up in person or virtually is entirely up to you. But yeah, I'm not, this will be a more traditional class setting in as much as I will lecture for usually between 45 minutes to an hour, and then spend the last 15 minutes of class answering any questions people may have, etc. There is no expectation of you have to watch an hour-long video before you show up to class kind of thing. Any other questions of that vein? All right, so back to the syllabus. I feel like we have discussed homeworks thoroughly. There will be a couple of design projects in this class. I will try to have the first one uploaded by Monday, as it will be pertaining to operational amplifier circuits, and I will give you some details with specifically what I'm looking for. They're not going to be too terribly involved. I used to assign them as strictly just part of a homework assignment, but for bookkeeping on the ABET side of things, it's going to make my life easier to just give them as an official design problem. So that's why I'm moving towards that paradigm. So the problem is going to be very similar to what you should expect in a homework problem type of understanding. It's just a specially designated problem so that I can check a box on a stupid form in 6 years. So, all right, exams. There will be 3 exams given during this course. Each will consist of a closed book notes portion to be completed in class. So that's kind of misleading. I will allow you an equation sheet on exam 1. You'll be allowed one, like the front half or the, you know, yeah, just one side of a 8.5 by 11 sheet of paper for which to write any and everything you care to write about op amps on it. I will be providing you with the equation sheet for the RLC circuit analysis stuff, just because we're going to be using an equation sheet for most of that I give to you early on. So it just makes sense that you would utilize that on your test instead of recopying a bunch of crap down and potentially putting an error on there. I'm just going to give you the exact equations I expect you to use for the RLC circuit analysis stuff. Exam 2, you can use the front and back of a sheet. Exam 3, you can use the front and back of an 8.5 by 11 sheet. So it's closed notes, but you are allowed to use an equation sheet. The exam in-class portions are taken in class here. So that means the test, typically, I work them in around 20 minutes, which means I think an hour and 15 minutes is plenty enough time for you guys to do it. I've never had anybody complain that they didn't have enough time. Students usually finish in between 45 minutes and an hour. That in-class portion of the exam is worth 70% of your exam grade. There will be a brief bonus question worth 5 points on each of those in-class things. So you can get 75 of your 100 points on the in-class portion. Then there is a take-home portion, which is worth 30 points, typically 3 problems. And those problems are much more complex and involve using either a computer algebra solver like MathCAD or doing a circuit simulation. So you'd have to use LTSpice. So the in-class portion is very, very basic stuff. In my opinion, of the difficulty of circuits 1 type of question. So nothing too terribly involved. Generally speaking, I might give you one circuit that'll have 5 different steps. And if you do the steps in order, it's fairly straightforward. If you do them out of order, I don't know why you're doing it out of order. I'm telling you not to do that right now. But anyway, the take-home test will be a lot more involved, roughly 1 hour per problem kind of thing. That might be a little long for some of them, but none should take you more than an hour. And they intentionally, I will ask you to apply some sort of computer analysis to go along with it. And you'll be graded on not only your work on the circuit analysis, but then how you use your computer to aid your analysis techniques. So part of your grade is being able to use MathCAD and or LTSpice effectively. On the scroll back down here. So notice where it says exam 1 here, I don't know if you can see it from that far. The take-home portion is due the 17th. So that is 5 days later. That should be, it doesn't matter. I have it as the 17th, so it'll be the 17th. So you got several days in which to do it, and it's due at 5 p.m. So you also have roughly 3 classes in order to ask me questions and all that kind of stuff if there's some part of it that you don't understand. And I believe I have things structured in such a way that you will never have a homework assignment due at the same time as a take-home portion of an exam. One thing that I do want to point out is that it is very likely, so let's say looking here, exam 1 covers all the way up to this lecture 12. Okay, so really it covers from lecture 2 to lecture 12. The exam is on Monday. The homeworks homework 10 is not due until the following Wednesday. So you will take the exam before the homework is due, but I still expect you to know how to do that stuff. Now, this particular bit of material would actually be only given to you on the take-home portion of the exam because of the level of complexity, but I still need you to understand it at least fundamentally before you take the test. So like what I'm trying to say is that sometimes material on a homework will not be due before you take the test on it, but it will always be assigned. So I'm not gonna make you do something you haven't seen, but I might make you do something that you haven't gotten to yet, and that's on you, if that makes any sense. I'm giving you a week to give you plenty of time to ask questions, but I can't wait until everything's turned in to give you the tests, or otherwise this class would last until July. So it's not gonna work. So sorry if that was a very long-winded way of trying to explain that. Hopefully I didn't confuse anybody too terribly much. All right, so the exams, like I said, 70% is the in-class portion, 30% is the take-home portion. The due dates for the take-home portions are already put on Moodle, are already included in the syllabus, and I'll go ahead and put the submission portals and all that kind of stuff up today so I don't forget about it. The weighting of the grades is as follows: 30% for homeworks, which means every homework is worth 1.5% of your final grade. The design projects are worth 10%, and then each of the 3 exams are worth 20% apiece. The grading scale in this class is anything above a 90% is an A, and I mean that explicitly. I do not curve, so an 89.99 is a B. All right, so very, very strict 10-point grading scale. Let's see, syllabus changes. I don't expect there to be any emergency notification system and COVID stuff, all boilerplate that you should be seeing and have seen on every syllabus this entire year. So I don't feel like wasting time talking about that. And then we have our schedule, which has the list of the lectures, the topics being covered, when the homework assignments are going to be assigned. And like I said, if it's assigned on Wednesday the 10th, it'll be due the following Wednesday at 5, et cetera, et cetera, et cetera. So any questions regarding syllabus junk? Yes, sir. So they are not night exams. No, they are to be taken in class. Because there's only one section, we just do it in class. I could, if there were enough desire for it, I could figure out a way to do a review session on an afternoon or something like that where you guys don't have a class prior to the exam. But I'm not going to do a review session on the days I have designated for tests and then make you guys show up that night. Because A, I'm not allowed because there's only one section of this class, and B, I don't want to piss off my wife any more than I already do by having to proctor other night exams. So, yes, sir.
These in-class exams, are they taken in this class?
Yep. I mean, I can try to find somewhere else, but you're literally the first person to complain, and I've been teaching this class in this room for 4 years. So, toughen up. I don't know. Yeah, I mean, there's no other room in Nethkin Hall that can accommodate this number of students. So I would have to find a room in the ISB or something like that that's open at this time slot on those days. And that's honestly more work than I'm willing to do. I don't know. The last time I did Circuits 1, I think we were still doing online tests because of the Rona. So I don't know. And those are always a pain in the butt to schedule anyway. All right, any other questions on the syllabus and all that jazz? All right, so close this guy out. And this guy and this guy. All right, so as part of this class, you will be expected to use MathCAD. I would prefer that you use MathCAD Prime 6.0. Although I do have all of the other versions on my computer as well, so I can open up your files and crap if you choose to not use 6.0. But this is the one that the most recent one that we have access to, so it's the one that I would prefer you use. Not gonna be a big deal if you choose not to, but you will be required to use MathCAD at several points throughout this class. Another software that we will be using is LTSpice. LTSpice is a circuit simulation tool. There's going to be a lot of you who are going to be like, damn it, why didn't they tell us about this while we were taking Circuits 1? And the short answer is because then you would never do any of your homework. Because if you only need the final answer, LTSpice is able to give it to you usually pretty darn easily, but it does not show any work whatsoever. It's a software package that does circuit analysis, and everything is done using nodal analysis. So we'll talk about that in a minute. So I have provided you with the download link, an overview of some of the functionality, and then a few tutorials. I am not saying that I am unwilling to answer questions regarding LTSpice, but I am also saying I am not IT. So like if you can't figure out how to get it set up and all that kind of stuff, don't come talk to me about it. And if you have questions about how to use it on a particular problem or something like that, I want to see that you've done work and tried to research things first before you come pester me about how do I do this specific thing. So if we look at homework assignment number 1, real quick here, this first problem is, in my opinion, fairly straightforward. No dependent sources or anything like that. And you're asked in part A to find the Thevenin voltage VTH, positive polarity on the left, negative polarity on the right. Part B, you're asked to find the Norton current, reference direction to the right. Part C, you are asked to directly find the Thevenin equivalent resistance. And I give you a hint there that when you turn off this 5 amp source, this 10 ohm resistor, this 10 ohm resistor, and this 20 ohm resistor form what's called a delta network that you probably don't know how to simplify just yet. So I ask you specifically to look up how to do a delta Y conversion and then do that. It's a very, very simple process. Wikipedia does a great job of explaining it and all that kind of jazz. It's not worth the 15 minutes it takes to explain it for me to do it. I'm just telling you that's how it's going to need to be done. Look it up. We're going to use it infrequently until we get to 3-phase power, and then we're going to be using it constantly. Part D, verify your answers using the Ohm's law relationship. Thevenin voltage is equal to I Norton times R Thevenin. And then part C, use the maximum power transfer theorem to determine some quantity, whatever. Basic Circuits 1 type stuff. Problem 2, more Circuits 1 type stuff, except you have a dependent source. More dependent sources. This time it's using test sources to figure out what's going on. And then we have some RL and RC circuits to where you have to do some manipulation and all that kind of crap. So very, very simple stuff, nothing more difficult than you were asked to do in Circuits 1. I want to take a moment to show you how you can use LTSpice to check your answers, okay? So what I have done is I have drawn the schematic diagram for problem 1. I've actually copied it down twice. Okay, so I have all my resistors and all that kind of jazz. A couple of quick things here that we could talk about very briefly about LTSpice. Most of the components are located up here, if you can see my mouse. The pencil is how you draw wires. This arrow is how you represent ground in your schematic. LTSpice, because it does nodal analysis, every single schematic you will generate has to have a ground or it will freak out and tell you that it can't do anything. This is for just labeling things. So I use it to label this node as VThevenin, so that when I do the simulation, it will just spit out VThevenin is equal to some voltage. Resistors, capacitors, inductors, diodes, and then this guy right here, which looks like a digital logic gate. I don't know how many of you have had 333 at this point, but that's the components button. So that's where you can find literally everything else, from op amps to voltage sources to dependent sources. All that kind of crap is tied up in here. This product is made by, I think it's Digilent now, but it was made by Linear Technologies and Analog Devices before that. So it has the SPICE models for a whole bunch of practical op amps that were made by those manufacturers and all that kind of stuff. So you will use this software package or one very similar called PSpice throughout your entire remainder of your EE career as a way to test designs and without actually physically blowing crap up. So it's very useful software package, and it's good to get introduced to it as early as possible to help you in other things. So if we have a voltage source or something like this, which right now this is a voltage source, if you right click on the component, that's how you can edit the values and all that kind of stuff. Inherently, it is set up to be a practical voltage source, meaning you can assign both a voltage value and a resistance. So you can use this to model practical voltage sources and all that kind of stuff. If you click the Advanced tab, this is where things get really, really interesting. You can do pulses, you can do sinusoids, where I want to point out that the frequency of the sinusoidal function, first, it's always a sine function. I know that we traditionally do cosine functions, but it's always a sine function. So you will have to change some parameters to make it a cosine function. Specifically, you have to change this phi value right here to minus 90 degrees to make it a cosine function. So you can give it a DC offset, the amplitude, and then the frequency is measured in hertz. So LTSpice always uses linear frequency, even though pretty much every textbook on circuit analysis uses angular frequency omega. So if you have a particular value of omega that you want to simulate, you need to divide it by 2 pi and then put that number there, or things aren't going to quite match up. So I just want you to be aware of that. Then we can do exponential voltage functions. I don't remember what SFFM stands for because I've never had to do it. This guy, PWL, is effectively you can string together short lines to make interesting looking voltage waveforms, or you could literally just upload a file. So these are all the different types of voltage waveforms that you can do. And then when we get into our steady state sinusoidal analysis, particularly looking at filters, we'll come over on this side and just make frequency a variable and all that kind of jazz. So this is a very, very powerful package. There are similar things that, no. There we go. Oh, and this was 20. Do a similar thing for currents, current sources. For resistors, you can put in the resistor value itself. You can assign it some tolerance and some power rating so that you can really simulate a practical resistor. So most of you guys learned in the Engineering 120 series that there's those 3 bands at the beginning that tell you what the resistor value is. There's a 4th band that tells you what the tolerance is. So I think silver is 2%, gold's 1%. And then the color of the resistor itself usually tells you what the power rating is. So if it's tan, it's a 1/4 watt. If it's kind of a light bluish green color, that's usually an eighth of a watt. Anyway, you can simulate all that kind of crap in here and see whether or not you're exceeding the resistor's power handling capabilities to see whether you're going to burn stuff out, yada, yada, yada. So we're not going to use nearly all of these practical functionalities in this class, but again, it is a very, very powerful tool. Excuse me. So for problem 1, parts A and B, I have set up a circuit on the left where I have just assigned a nodal voltage of VTH to terminal A and assigned ground to terminal B. And if I simulate this using what's called a DC operating point simulation, this tab all the way over here to the right, what happens, excuse me, is it pops up a window and it tells me that the voltage at node VTH with respect to ground is 20 volts, which means the Thevenin voltage is 20 volts. Doesn't give you any of the work that was required to get there, just gives you a means by which you can check your answer, okay? For the Norton current, and so this is something that's kind of important here, it can only tell you the voltage drop across a component and the current, so it only gives you the voltages at nodes with respect to ground. So if I mouse over this region of wire right here, down here at the bottom, it says the DC operating point of node 4 with respect to ground is 20 volts, which makes sense because between this point right here and ground is exactly 20 volts because it's defined by that voltage source. I can move my mouse over to this point. Now this node is VTH, it says it's 20 volts right here. This happens to be node 3, 22.5, blah, blah, blah. It randomly, that's not random, but it assigns a node number to any node that you don't tell it this one has a specific value. So that's why only this one is VTH. The rest of these are assigned from the top left, starts at node 1, and then it works its way from left to right, top to bottom, assigning all the other ones numbers. So, excuse me, by choosing my ground terminal to be at node B and my A terminal to be VTH, this is allowing me to directly calculate the Thevenin voltage for this guy. On the right-hand side here, what I have done is I have placed a voltage source that has a value of 0 volts here to represent my short circuit. And the reason I have to do that is because if we mouse over a node, which is any wire, it's only going to give us the voltage. It doesn't give us current. If we mouse over a component, it tells us the amount of current that flows through that particular component. And in our DC operating point analysis, when we make it spit out numbers, that's how it does things as well. It tells you I, open parentheses, and the component label saying that the current that flows through this particular component has this value. So I can't simply draw a wire here, or there's no component for me to take the current flowing through. So I threw a 0 volt voltage source, which is the exact same thing as a short circuit, and it gave it to me. I could have also just put a resistor in that had a very, very small value. It freaks out if you put a resistor of 0 in. So you could put like a 1 picofarad, or excuse me, 1 pico ohm resistor, 1 times 10 to the negative 12 ohms, and it'll treat it as essentially a short circuit. So anyway, LTSpice can be used for simple DC circuit analysis using this DC operating point simulation. It's fairly straightforward. I highly encourage you guys to play around with it. To do dependent voltage sources and dependent current sources, you go into the component window and you type in B, and then it's going to be BI, which is a behavioral current source, which is their way of representing any dependent current source. And so let's click on BI right here and just drop one in. I is equal to F, where F is just a mathematical function. So you literally tell it what math you want it to do. So it could be twice the voltage drop over a particular resistor or something like that, however you want to do it. So And there'll be a very similar thing for behavioral voltage sources, which are found by using BV. So that's how you take care of all of your dependent sources. So you can do all of the DC circuit analysis very, very trivially. The transient analysis that we're going to do is a little bit trickier. Let me close this guy out. Let me move this thing out of the way. So this is a simple, or how you would model a simple RC circuit for T greater than 0 plus. So once you know the initial condition, this can simulate everything past that point. So if I had a circuit, which when the source got taken out was simply a 2.7 kilo ohm resistor in parallel with a 90 microfarad capacitor, and I knew that the voltage across my capacitor at T is equal to 0 minus was 5 volts, I can do what's called a transient analysis, which is just simply plotting functions with respect to time. And for this particular circuit, because it's an RC circuit, somebody with a calculator tell me what the time constant is supposed to be. There's only an R and a C, so this should be pretty trivial, I hope. Yeah, 243 milliseconds. So this number right here after tran is how long I am telling it to do the analysis for. So with a time constant of roughly 1/4 of a second, 5 time constants is roughly 5/4 of a second. So that's why I chose that particular value. That's going to be long enough for me to see it decay, but it's not going to decay so quickly that I can't see exactly what's going on. So if I run my simulation here, it gives me a blank screen, and then I click on either, if I click on the component, this is a current probe, and so it's telling me the current that's flowing through the capacitor in this down direction. Or if I came over here, this would be the current flowing through the resistor in the down direction. Or I can click on the node, which is going to tell me the voltage at that particular node. So my capacitor voltage, I can see that it starts at 5 and decays to 0 in around 5 time constants, which is exactly what I would expect. How does that help me with my homework? Well, I can right-click the plot and click Add Traces. And this box right here where it says expressions to add, I can literally type in a mathematical formula. So I know that at T is equal to 0 minus, I have 5 volts. I'm going to multiply that by an exponential function, exp, open parentheses, negative. So now I need tau to the -1, right? So 1 over 0.243 is 4.115226. There's some more digits, I don't really care. Multiply by time. And that's how I can check my work. This blue curve is exactly on top of the green curve of the simulation, meaning my analytical solution that I got by doing circuit analysis exactly matches the simulation. So any transient analysis problems that you can do, or that you are asked to do, you can always check your work on those as well. When we get to steady state sinusoidal analysis problems, I'll show you how you can use LTSpice to check those. So you have a tool by which you can check, I would say 90% of all of the homework assignments that I'm going to give to you, or 90% of all the problems I'm going to give to you. You have a tool by which you can check to see whether or not you got the right answer. And that's not going to be able to tell you where you made a mistake if one was made, but you can definitely see whether or not a mistake was made, period. So at least it'll help you with hunting things down. So LTSpice, like I said, very, very powerful tool. We're going to use it for lots of things, but this is one of the primary roles it's going to play here as figuring out whether or not you screwed something up. It's a great tool for that. So any questions on anything else today? All right, nobody's saying much anything, so I'll see you guys on Friday where we will start talking about an introduction to amplifier circuits and developing the practical op-amp model. So effectively, we're going to throw away everything that you learned about op-amps in Circuits 1 and rebuild faster, better, stronger. All right, see you guys on Friday.